Okay, so thank you for coming back. Here are the afternoon sessions starting now, the English one. And now we have a group of guys from the Politecnico of Torino quantum team, the QubiTo team. They are talking about quantum oracles. So we are starting, of course, with some basics on quantum computing because you know it's tough stuff. And then they will lead us in a journey with quantum oracle. So thank you, and I leave you the floor.
Hello everyone, my name is Francesca. They are Enrico and Giorgia. And we are first year master's degree students in quantum engineering at Politecnico di Torino. Today we are here to represent our student team called QubiTo, which was born this year in April and which is supported by our university, Politecnico di Torino. So, who is part of this team? We are students from Politecnico di Torino. And as you can see, we come from different backgrounds. Some of us are undergraduate students, some of us join master's programs, and also PhD students, researchers join the team. Some of us are studying quantum engineering, others electronic engineering, computer engineering, aerospace engineering, physical engineering. So we can say that the diversity of our university careers is our strength point, because each of us has the opportunity to cultivate an individual curiosity towards quantum world. And so the overall vision of the team is very eclectic and varied. So as a team students, we of course share some common goals. The main one is also the reason why we are here today. So we want to excite people outside our university environment to quantum world by sharing our knowledges. We are also ambitious. We aim at participating in international and national hackathons, competitions, because on one end they give us the opportunity to let our team be known, and on the other hand we have the opportunity to challenge ourselves, to grow as a team, to share opinions and to strengthen our strength points. So the team, last but not least, has also the objective to group people of common interests. So we are born this year in April, as I mentioned before, and these are the achieved results up to now. Some of us joined the Qiskit Global Summer School, and others went to the event in Bologna. And in both activities, we place at good ranking in the overall classific. So, someone of you may ask now why the necessity of develop quantum computing. So, the basic and most immediate answer is that quantum computing is a strong means to solve basic problems that are very complex for classical supercomputers. And so in quantum system simulations, in problems optimizations, in machine learning, database search, quantum computing is now plays nowadays an increasingly emerging role. And here we propose you an example. This graph shows you the complexity analysis correlated to the three main ways to compute Fourier transforms. So as you can see, the quantum Fourier transforms is the algorithm with the less complexity analysis. It is the fastest one. Here n represents the number of samples that composes your systems. But quantum computing involves also some other disciplines. As you can see, these are just the main application domains. They are not strictly correlated one to the other. You can see that they range from molecular chemistry to cryptography. And especially in molecular chemistry, quantum computing enables us to simulate the behavior of molecules. And so in the drug discovery and the development in the pharmacological world, it is very, very, very efficient. And thanks to these multiple advantages on very fronts, also many countries are investing in this field. So as you can see, Germany, China, United States, Europe in general are investing to develop quantum computing. And you can see that in 2021, the investments on quantum computing doubled the year before. So now we go in deep details about the basics of quantum computing. So where does the idea of simulating the nature through quantum mechanics born? So Richard Feynman states that nature is non-classical. So why don't we try to simulate it through quantum mechanical laws? And from this idea, a real paradigm shift happens. So we basically have passed from transistors, which are characterized by binary systems of 0 or 1, to the qubit, which is the fundamental unit of quantum computing. It is a binary system characterized by infinite combinations of 0 and 1. So the qubit is, as I said before, the basis of quantum computing, and it is characterized by two quantum mechanics phenomena, superposition and entanglement. Any state is graphically represented inside this sphere, which is called the Bloch sphere. And so superposition in particular is the linear combination of two basis states. The two basis states are ket 0, which is basically the north pole of the Bloch sphere, and ket 1, which is the south pole of the Bloch sphere. And so by superposition, you can express a generic state ket psi as a combination of ket 0 and ket 1. And in the formula, alpha and beta are called amplitude probabilities. They are complex numbers, and they have to satisfy the normalization condition. So the sum of their modulus squared carries 1, because the modulus square of alpha and beta represent the density probabilities. The entanglement instead is a quantum phenomenon discovered by Einstein, Podolsky, and Rosen in 1935. Basically, the idea is this one. You have a system made up, of course, of some constituents. You cannot consider the quantum state of a single constituent be independent on the quantum states of the other constituents. And this bond, this correlation, is implicit in the quantum state of the constituents. So even if you try to separate them, to put them apart by long distances, entanglement ensures you that the quantum states of both are always correlated. And superposition and entanglement together is the key, the strength point of quantum computing, because you can perform parallel computations on multiple data. And here we propose you a table of comparison between classical algorithms and quantum algorithms in terms of complexity analysis. Here you have the most important computer science problems. And as you can see, in any cases, quantum algorithm ensures you a fastest procedure. According to me, it is illuminating the case of factorization in prime numbers. As you can see, you are basically passing from a polynomial kind of complexity, and to the third, to a logarithmic one. So it is so impressive. So now I leave the floor to Enrico, which will explain you better the Grover search algorithm. Thank you.
Hi everyone, I'm Enrico, and my purpose here is to make a brief discussion about the Grover algorithm. The Grover algorithm is defined as the quantum search algorithm, whose purpose is to find an element in an unordered list of elements. So the main phenomenon exploited by the Grover algorithm is the superposition between the different qubits. The quantum oracle is the fundamental block of the Grover algorithm. So this is defined as a black box that is capable of giving us the solution of our problem. Just like in this image I put the Delphi oracle. There is just like something that can give you an answer to a question that you don't know the answer about. So basically, the quantum oracle is capable of giving you the answer of a certain problem. In general, we define a problem in a logic way with a Boolean logic. And for example, here I put as an example as a problem to find the elements greater than 3. So here, as an example, we have 2 as an input. The output would be 0 because the function is not true. While in the 4 case, we have 1 as an output because the function is true. So 4 is greater than 3, then the function will be equal to 1. The important thing to understand is that the quantum oracle exploits the superposition to evaluate all the qubits all at once, because we can prepare the qubits in the initializing state, and after that, when they are all superposed together, we can evaluate all them all together. So this is done by a Boolean function, and in order to understand our Boolean function, I would like to present you a brief discussion about the Boolean logic, and particularly the difference between the classic case and the quantum case. We all know that the Boolean logic in the classical case is exploited by 3 main keys. Namely, they are the NOT, the AND, and the OR gate. They are called the universal because by constructing them all together, we can construct all the other gates in the classic Boolean logic. While in the quantum case, we have 3 fundamental ports. There are the NOT gate, the control NOT, and the Toffoli gate. So the NOT is equal to the classical case, but in the control NOT, we have this example right here that explains you very well how it works. We have 2 types of qubit. The first one is called control qubit. That is in the upper side of this gate. And the downside, there is the target qubit. In the first example is 0 and 1. So we have that if the control qubit is equal to 0, the state of the second qubit would not be changed. So here we have that the output is equal to the input. But if we have that the control qubit is equal to 1, the target would be changed. So from 1, it would be equal to 0. And other gates are the Toffoli gate, that is a control with multiple controls, and the Hadamard and the Z gate. The Hadamard and Z gate, just like all the other gates, qubit gates, act on the state of the qubit, namely on the position of the state on the surface of the block sphere. The block sphere, as Francesca said, is a representation of the qubit. So we can find the exactly state of our quantum state in that position on the surface. So the Hadamard gate is the function of the Hadamard gate is to apply a rotation on a certain axis of pi over 2 degrees, and After that, we can apply a z-gate that applies a rotation around the z-axis of pi degrees. Before moving on, we have to make an assumption of understanding the difference between two types of oracles. The first one is a Boolean oracle, and it evaluates the function that is fx on one single qubit that would be for us named as ancilla qubit. And the phase oracle is the oracle that maps the function, the Boolean function, and it exploits this function as a sign flip of our solution. Because we all know that the information coming from a quantum algorithm is probabilistic, so we have to manipulate the distribution of probability, and you know, it's some steps in that. And so in the first step, we have to initialize all the probability amplitudes of our combinations. So here the register is made by 4 elements, and because we are using 2 qubits, the number of the elements of a quantum register is made by 2 to the n qubits. So here in this example, it's 2 qubits, and we are 4 elements. In the first step, so we have the equiprobability made by the Hadamard gates. After that, we apply in the step 1 the oracle, our oracle, whose function is to make a sign flip of our solution, just as I said with the phase oracle before. And after that, we apply the last step, that is the diffusion operator, that is made by these Hadamard gates, NOT gates, control Z, and the opposite, in order to sign flip another time the probability amplitude of our solution and to amplify it. So in overall, the probability amplitude of a solution will be amplified, while the non-solutions will be less amplified. And so this is not finished for our algorithm, because the step 0 is repeated only once. So for this reason, it's called the initialization step, while step 1 and step 2 are reiterating an optimal number of times. In order to do that, we can exploit a proof, a geometrical proof, in which we have to define as initial state the equiprobable superposition between the states after the step 0. So after we applied the Hadamard gates. After that, we define, we start to make this geometrical proof by defining this vectorial space spanned by the 2 vectors S prime and W. S prime is defined as the linear combination between the non-solutions, while W is the solution of our problem. So our main purpose is to get the vector S, that is the initializing state, as near as possible to the W. So in order to do that, we apply the oracle operator that is making a reflection around of S with respect to S prime. So we are in the state UWS. After that, we apply the diffuser in the step 2, and we get a state that is in the position US UWS. And so we can appreciate that before applying the Grover algorithm, we were in the theta half position, while now with the angle, we are with the theta plus theta half. So step after step, we can go nearer and nearer to the W, but we have to pay attention, because if we apply a number of iterations that is larger than the optimal number, we can get not close, but also past our solution. So we can not also be near, but also get farther from that. This is the number of the solution, making the assumption that we reach exactly the solution with the vector, and this is equal to pi over 4 times square root of n over m minus 1/2, where n is the number of the elements in our list, that is equal to 2 to the n qubits, while m is the number of solutions of the problem, so the number of solution that must be flip signed by the oracle each time. And now I leave the floor to my colleague Georgia.
Thank you, Enrico, for your introduction. I'm Georgia, and I now bring our personal experience. What do I mean? up to now, Enrico has introduced the main steps of Grover algorithm. And now, as engineers, we want to delve into practical applications. And moreover, as a team, we need to give results to Politecnico. So we have to compete in international competition, so we need to get ready. How can we do that? We had the idea of making an internal hackathon. A competition that, what is an hackathon? A competition that typically involves programming, and of course a lot of problem solving, team working, and so we had the occasion to know each other better because we split into smaller groups. It's a newly born team, so we had to know what potentialities are within our group. And so we had the occasion to solve real life problems, and of course we learned by mistakes. So what was the task? We had to solve a problem using Grover's algorithm, that is a search algorithm. So which kind of problem? We had to find it, of course. It was part of the challenge. And this freedom gave us the possibility to come with different ideas, original ones. And some of us proposed finding among alphabet letters the letters of a word. For example, QubiTo. Or, for example, somebody proposed to the graph coloring problem. Or the last two, the shareholder combinations and the piano problem, are the ones that I'm going to explain better, just for brevity, just these two ones. And so, what is these shareholder combinations? Imagine you have a company, and there are 3 shareholders. One of them, A, holds 50% of the shares, whereas the remaining part is split into B and C. Which combination of shareholders satisfies 2 requirements? There are at least 2 shareholders, and there is strictly more than 50% of the shares. How can we solve it? How did we solve this problem? We modeled the problem in this way. Each shareholder is represented by a binary variable. 1 if the shareholder is present, 0 if not. And so the 3 possible combinations are all of them, and so 1, 1, 1. A and B, so 1, 1, 0. And A and C, that is 1, 0, 1. We found the Boolean expression, and using some Boolean algebra, we came to AB, A and B, or A and C. We then need to implement our Grover circuit, and the first step of the circuit, as Enrico explained, is, of course, understanding how to build a Boolean oracle. So, we have, first of all, we have the 3 gates H that initialize the state. Why 3 qubits? Because we had to represent 2 to the 3rd, 8 cases. And so the first 3 qubits are data qubits that encode the states where we want to explore. So we make the first computation, that is A and B, through this Toffoli gate. And we store this result into the first ancilla qubit. Then we compute A and C, and we use this second ancilla qubit. We then sum the result doing an OR gate, A and B, or A and C. And this last ancilla qubit stores the final result. We then do the symmetric gates with respect to the OR, and this is our Boolean oracle. That is just the first step to put here into this bigger green oracle, which is the face oracle. So Boolean oracle, then the flip Z gate that flips the solutions, and then the symmetric with respect to the first one. This is the face oracle, and then we have the so-called diffuser that Enrico explained amplifies the solutions. So these green blocks and the blue one all together represent one iteration. How many iterations we need to do to understand what's the solution? Well, it depends on number of solutions and the possible items. In this case, we did it once. So these are already the solutions. We repeated twice, and in this case, we are amplifying the non-solutions. We did for the third and last time, because this is the maximum probability of obtaining the true solutions. This is the best and optimized number of interactions. You can do more iteration, but the probability decreases. So this is the best result you can obtain with this oracle. And that was just the first case study. The second one instead is a piano problem. We want to find the notes belonging to the C scale that are the white keys. We encoded each key into a combination of 0 and 1s. How many qubits we need this time? Well, 3 qubits can represent at most 8 cases. Here instead we have 7 solutions and 5 non-solutions. That's why we employed 4 qubits, and that's why the first key, C, is all zeros, then 001, and so on. And the solution is just CD and all of these states. That, translated into a Grover circuit, means all these gates. Each gate represents a solution. And then we do an OR, summing all of them. This is the Z gate. We mirror the Boolean oracle, and that's how we obtain the phase oracle. Then, the same as before, the diffuser. And this is an interaction. How many interactions in this case? Just once, because as Enrico told you, it depends on some parameters, and doing the computation, it results exactly 1 iteration. And so, these are the 2 cases that we are bringing you today. Although they may seem simple, they helped us understand in better way the Grover algorithm, because knowledge is not enough. We have to put hands on. And so that's why we tried with our hands, and we had, so what we did in this occasion, we started from quantum computing in general. We focused on a specific topic because we have to start from somewhere. So we started with Grover's algorithm, and it's just this is just our first step. This is the first step of our journey, because quantum is a new world, needs to be explored. So the key is that we believe in quantum, and you. Thank you for your attention, and now we are here for your questions. In this case, for example, at first iteration, we already have 28% of obtaining the true solutions. Going on, we obtained 33% of obtaining the right. Then this is the highest probability. Because we have to do many measurements of a quantum circuit. So on average, you still obtain sometimes the non-solutions, but on average, the solutions are these three. So over 8 cases, we obtain with almost 1/3 the solution that is 1, 1, 0, 1, 1, 1, and 1, 0, 1. So I don't know if this was the question.
Yeah, no, I was wondering, like, I figured you need to repeat the algorithm multiple times to weed out errors, if there were any. I just wanted to know what was the range of error with respect.
It depends on the problem sometimes, because number of solutions and number of items. Do you want to say something?
Have you tried to implement this two-solution on an SDK, a quantum SDK, and in case you have used an actual quantum computer, quantum backend, which kind you have used?
I forgot to say that this is a Quirk interface. So this is just a graphical interface. We just have the results, not the complete histogram of probabilities. We may have tried, we tried to use a Qiskit, but we had some problems.
Yeah, also on Qiskit you can try with the simulation, not only on local, but also with the quantum computers all around the world on the cloud. But we didn't try with that. We only use these simulations.
Probably in the second case, you have the width of the circuit was too,
Yeah, exactly. Yeah, yeah.
so you need a premium subscription.
Yeah, I think so. Because I tried with IBM, but it doesn't sustain a TOEFL gate with 7 controls. So it's not useful in that situation.
Probably it's due to the topology of the computer itself. It was connected that much QubiTo network. But a multi-control NOT gate in that case could be harder if you have a not so connected topology to swap to function. Makes sense. Thank you very much.
Thank you.